we've seen that dissolving a solute in a solvent affects the vapor pressure, and that will directly affect the boiling point, right? We know that the definition of boiling point is the temperature at which the vapor pressure of the solution equals the atmospheric pressure pushing down. If you lower the vapor pressure of a solution, or by adding solute, that's going to raise the boiling point of the solution. So here's the normal boiling point of water, right? The solution is going to have this phase diagram. So here's our phase diagram, solid, liquid, vapor, right? And so what happens is the boiling point of water is here, right? The boiling point of a solution increases, right? And so the change in boiling point will be the boiling point minus the normal boiling point. Right, and so the equation to calculate boiling point elevation, one of the colligative properties we're studying, right? As you dissolve stuff in a solution, the boiling point of that solution goes up. So delta T boiling, right? This is read as the boiling point elevation is some constant, the boiling point depression constant, times the molality, right? The moles per kilogram of solution. They have tables of these. Freezing point and boiling point elevation constants. So you can see they're specific to the solvent that you're studying. So if you're looking at water, right, by making a solution, the normal boiling point of water is 100 degrees Celsius. This guy will help us calculate the new higher boiling point. If you're studying benzene or ethanol, they have different values. And it's the value for the solvent is the important part. Remember, with colligative properties, it doesn't matter what you're dissolving. Right? It's just how many of those particles have dissolved in the solution. So the kind of calculations we can do are this. So again, boiling point is the temperature at which the vapor pressure of the solvent or the solution, P naught. So right, this would be the normal vapor pressure is equal to the atmospheric pressure. Right? As solute is added to the solution, the boiling point increases. Right, as given by this equation. So boiling point elevation equals I. We're going to talk about this kind of a little bit. This is called the Van't Hoff constant. And for most molecular compounds, it equals 1, so we don't have to worry about it right now. There's our constant from the table, right? We don't have to memorize these, but we'll have them. And this is molality. Remember, molality is moles per kilogram. So moles of solute per kilogram of solvent. So a little bit different than molarity. But let's see here. Okay, so what's the boiling point of an antifreeze coolant solution made from 50 grams of water and 50 grams of ethylene glycol? Okay, so the normal boiling point of water is 100 degrees. Right, we don't want it to boil in your radiator, so we put antifreeze, which actually helps it not boil too, to raise the boiling point up. So if I want to calculate the boiling point, I need to know the change in the boiling point, which is the boiling point elevation, equals, I'm going to write I, KB times M. All right, and what do we know? So we want to solve for this guy. We know this is going to be 1 for molecules. Constant boiling point elevation constant is 0.5121 degrees C per molal, and the molality, M, is what we need. So let's go over here and solve for that. So molality is moles of, in this case, ethylene glycol per kilogram of water. So how many moles of ethylene glycol do we have? Well, we got to calculate it. Let's go down here to do that. So moles of ethylene glycol, it's going to be 50 grams of ethylene glycol. And to go from grams to moles, right, we do our conversion. 1 mole is, convenient, that was 7. Okay, if I mash that in, I get 0.0806. 0.806, I'm sorry, moles of ethylene glycol. Okay, the molality, though, is up here, so now we know we have 0.806 moles of ethylene glycol. How many kilograms of water do we have? Well, 50 grams of water, grams to kilograms, exactly 1,000 grams. So I divide that, 1, 2, 3, okay. So 0.050 kilograms is the molality. I can mash that in, and I get 16.1 molal in ethylene glycol. Whew. All right, so now we can plug that in here for the molality. All right? And so, as we know, in our equation, we have to make sure our units are right, and they are. So molal will cancel molal, little m's. We'll be left in degrees Celsius. So the delta, the change in the boiling point will be 8.24 degrees Celsius. All right, and so this is the change, right? And this is important, right? Delta means change. So if it asks for what the change is, then we know the boiling point is going to go up by 8.24 degrees Celsius. But if it asks what is the new boiling point, which is what this wants, we have to add this to our normal boiling point, right? So the normal boiling point of water plus the change in boiling point will be the new boiling point. We know 100 degrees Celsius is the normal plus 8.24 degrees C. 108.24 degrees Celsius is the new boiling point. So now this boils at 108 degrees instead of 100 degrees. All right, so that's boiling point elevation. Freezing point depression is basically the same thing. All right, we saw by making a solution, the phase diagram changes again. This is pure water. Now this is the solution. As we start dissolving things, this is shifting this way, so we have a new lower freezing point. So it's boiling point elevation and freezing point depression. These equations are the same thing. The only thing that changes is you call this F instead of B, and this is a different constant. Instead of the boiling point elevation constant, it's the freezing point depression constant. Otherwise, everything's just the same. You just need to know which way the freezing point is going to go down, right? It's freezing point depression, so it's going down. Boiling point elevation goes up. All right, so we're preparing a solution, condensing 4 liters of gas, some temperature and pressure into benzene. Okay, benzene has a normal freezing point of 5.51 degrees Celsius. Calculate the freezing point of the solution. Okay, so we have benzene, right? We have a thing of benzene, and we're starting to dissolve something in it. And it doesn't matter what it is, as long as it's molecular in this case, so I equals 1. And in the previous problem for the boiling point elevation, you were just given the grams of ethylene glycol, so you could calculate the molality. This one's more fun because you're given pressure, volume, and temperature. So what do we use to calculate the moles in the solution now? Right, Pivnert it is. So P, let's convert this, 748 millimeters of mercury. Remember, it's got to be in atmospheres. So 1 ATM equals 760 millimeters of mercury. Mash that in. 748 divided by 760 equals 0.984 ATM. Okay, so that's going to go here, 0.984 atmospheres. The volume of our container is 4.00 liters. N is what we're solving for. R is the universal gas constant. Liters, atmospheres over moles, Kelvin, right? Don't mistake it for this guy, 8.314 joules per moles Kelvin. We use this guy for energy. We use this one for pressure. And the temperature, oh my gosh, 27 degrees Celsius. So we got to turn that into, I don't have enough space, 27 degrees Celsius plus 273. It's got to be in Kelvin, right? Am I adding this in? It's going to be 300. 300 Kelvin. All right, after all that, so what I'm doing is, right, in my calculator, I'm multiplying these guys together, and I'm dividing by this guy and dividing by this guy. So 0.984 times 4 divided by 0.0821 divided by 300 Kelvin gives me 0.1598. 0.1958 moles of mystery gas. Whew. Okay, we're getting closer. We still need to know delta TF equals IKF times M. We still need the molality. Molality is still the moles of gas, in this case, over kilograms of benzene. And so it's going to be 0.1958 moles over, disaster, over kilograms of benzene, divide by 1,000, just like we did in the previous problem. Kilograms by 0.058, 2.7 molal. So the freezing point depression will be 1, because it's a molecule, although I didn't tell you in this problem. Bad work by me. The freezing point depression constant of benzene is 5.12 degrees C per molal, and the molality is 2.76 molal. And, okay, mash that in, times 5.12, I get 14.1 degrees C. This is the freezing point depression. Remember, this is how much it's going to go down. The normal freezing point is 5.51 degrees Celsius for benzene, right? This isn't water. Degrees C, so minus 14.1 degrees C equals negative 8.60 degrees Celsius. So this is the new freezing point of the benzene after we dissolve this gas in there. Right? Again, we're just using the equation, right? The freezing point depression equation, which is basically the same as the boiling point elevation equation. But I gave you molality in a fun way using PV equals nRT. Super fun, right? All right, one more problem here. The addition of 1.25 grams of an unknown compound to some benzene produces a solution with a new freezing point. What is the molecular weight of the unknown compound? Fun. Okay, so molecular mass or molecular weight is in what units? All right, from the periodic table, we know it's the mass in grams per mole of the compound. So we need to know, well, look at this. We know there's 1.25 grams of this unknown. The question is, how many moles are there? Well, you're using freezing point depression to tell me. So delta TF equals I KFM. It tells me the new freezing point is 4.52. Okay, what's the change in freezing point? The normal freezing point of benzene is 5.12 degrees Celsius, right? If the new one is 4.52 degrees Celsius, how much lower is it? What's the freezing point depression? I'm getting 0.6 degrees C. I is 1. What is the freezing point depression constant for benzene from the previous problem, right? Not something you have to memorize, but I gave you on this page, so there we go. And now the molality. So let's solve for molality. M equals what? 0.6. Right, oh, and delta F. So it goes down by 6 degrees Celsius. Just don't worry about signs in these problems. Right, we know the direction the temperature is going to change. Freezing point depression, so the new freezing point will be lower, but there's no negatives or positives. So we just use absolute values for all this stuff. So 0.6 divided by 5.12 is 0. Let's see how this goes. I don't know. We'll see. 0.117 moles per kilogram of benzene. Right, that's moles of unknown. So if I had a kilogram of benzene, I would have that many moles. But how many kilograms do we have? 85 grams. Uh-oh. Gonna be late. All right. So that's gonna be 0.085 kilograms. And what happens there? If I multiply by the actual number of kilograms, then I'm left with the moles of the unknown. So let's mash that in. Times 0.085 gives me go back. 0.00996 moles of unknown. And, oh no, this is a disaster. Hold on, what happened here? 5.12. Oh, what a clown. Clowny clown. Got to read more carefully. 5.51 degrees C. Yep. 4.52. 0.99 degrees Celsius. 0.99 degrees Celsius. Bad work by me. Erasing. Okay, so one more time. 0.99 divided by... Stop. 0.193 moles per kilogram of benzene times 0.085 kilograms of benzene gives me moles 0.0164 moles of unknown. Okay, and the whole point of this was to get this guy so we could plug it in over here. So 1.25 grams over 0.016. Yeah, I should go to 2 sig figs here. Gives me 1.25 divided by 0.016. 78.1 grams per mole is the molar mass of this unknown. Whew. All right, so because we knew the freezing point depression, right, that's a measure of molality, we were able to figure out the number of moles by using the actual kilograms of the solvent. And this is what we're doing in lab. We're going to take water. Let me see, is this worth doing? Let's try. So we're going to take some water, right, in some kind of test tube. Right? We're going to measure the freezing point depression. So you're going to put a thermometer in there, right? And we're going to measure cooling curves. So it's going to cool and then it freezes. And remember, when it freezes, it should be a temperature constant process. If this is pure water, we expect it to be pretty close to 0 degrees Celsius. Then what we're going to do is put some solvent in, or some solute, some unknown in there, right? You're going to weigh how much you put in there. You're going to make a solution. So what should happen to the freezing point? It should go down. Right, and so then what we see is something like this. Oh, put a little supercooling in there. That's pretty cool. Right, so now we have a new freezing point, and the difference between here and here, right, don't use this, is the change in freezing point. Then we can use delta TF equals I will be 1, KF times M. KF will be for water. See this, and from there you'll be able to solve molality, right? Equals moles over kilograms of water. If you multiply by your kilograms of water in here, right, you'll be left with moles. Take the grams you had in the beginning, grams divided by moles equals the molar mass. It's going to be awesome. You're going to love it. Whoa, wrong button. All right, osmotic pressure in colloids next.